In this video, I want to go about proving the Archimedean property, which I'll define in two parts here for us. For this first part, given any number x, real number x, there exists a natural number n such that n is greater than x. The second part of the Archimedean property is given any real number y, and y is positive, there exists a natural number satisfying 1 over n is less than y. And let's start by proving this first part. And the second part actually is really easy to prove given the first part. So let's just prove this first part. Given any real number x, we can find a natural number greater than x, which is a pretty intuitive statement. It should be true since natural numbers, they're unbounded above. We can find a natural number larger than any number you give me. Okay. So, probably the easiest way of proving this is by contradiction. Just my cup of tea when we have a common statement that we want to prove in analysis, real analysis. The best way of going about it, if it's, this intuitive statement that is almost common sense, is to do a proof by contradiction. Why is that? It should be fairly easy to come up with a contradiction if we assume the negation, if we assume that this statement is false. How would the statement be false? So we would say for all x and r becomes there exists a natural number, there exists a real number x such that for all natural numbers n, we've got that n is less than or equal to x, which is actually, the opposite, the negation of what this is saying. So let's assume this is true. And this shouldn't be true. This is saying that we can find a real number that's larger than all the natural numbers. Well, all the natural numbers are positive, and if x is greater than or equal to all the natural numbers, we can say that x bounds the natural numbers. We'll say x bounds the natural numbers from above. Oops, whoa. From above. And here's my little number line that I've got down here. And let's say all of our natural numbers are hanging out over here, and we're assuming we've got some x that bounds the natural numbers. So all of our natural numbers are going to be to the left of this x right here. Okay. By the axiom of completeness, which we'll assume, or it's also called the completeness axiom of the real numbers, this tells us that n, being a bounded set from above, satisfies the fact that the supremum of n, which I'll call alpha, exists. If n is bounded above, if the set of natural numbers is bounded above, then the least upper bound exists of those numbers. And, visually on my number line, even though this isn't necessarily part of the proof, I like using it to think through the proof, alpha would probably be living right there. If the supremum of n exists, what does that mean for anything less than the supremum of n? For example, what if we are talking about alpha minus 1? Well, alpha minus 1 can't be an upper bound by the definition of the least upper bound. Since alpha is the smallest upper bound, anything smaller can't be an upper bound. Therefore, we can find there exists some, I'll call it like n naught. We can find a natural number such that alpha minus 1 is less than that natural number n naught. So on our little picture, our number line, here would be alpha minus 1. We would take a step back, and then we can find a natural number greater than alpha minus 1. It looks like this natural number would be alpha. Again, not necessarily part of the proof, but visualizing through it, n naught would live right here, same place as alpha. Anyways, well, here's the little trick, right? Let's add 1 to both sides of this expression and solve for alpha. And we get that alpha is less than n naught plus 1. Where would n naught plus 1 be? It'd be here, right? This would be n naught plus 1. Move to the right one. We've got a problem. We assume that alpha is the least upper bound for the natural numbers. In other words, all the natural numbers are less than or equal to alpha. However, we just found a natural number, n naught plus 1, that's greater than alpha, meaning that this alpha cannot be the supremum of the natural numbers. In other words, the supremum of the natural numbers cannot exist. The natural numbers cannot be bounded above. So does not, I'll write here, does not bound natural numbers from above. This statement is false, and we have completed our proof by contradiction. Therefore, we have proven this first part. Since natural numbers are not bounded above, any real number x has a natural number larger than x. I'll clear up some wiggle room for the second part, which is actually really easy to prove since we've shown this first part. I'll show you how we're going to do the second part. Given any real number, positive real number y, there exists a natural number satisfying 1 over n is less than y. It makes sense that y is positive, right? If y was, negative, like -3, we probably couldn't find a natural number less than -3 since all the natural numbers are non-negative. So we'll just deal with positive values for y. Again, I'm going to use my number line. Maybe this is 0, and here's our y. The statement is saying, and this is a really important statement, especially in real analysis when we talk about sequences. The statement's saying that between any, between 0 and any positive number y, we can find the reciprocal of a natural number. We showed that, natural numbers are bounding above all the real numbers, but now we've got kind of an opposite, a complementary statement that is going to be really helpful talking about sequences. But that's a bit of a spoiler. This is pretty easy to prove. Since we've got this first part, let's just talk about 1 over y, the reciprocal of y, which is also greater than 0. 1 over y is a real number, so by part A, or I guess by part 1, there exists a natural number, I'll just call it n, such that 1 over y is greater, or actually is less than n. Our natural number is greater than 1 over y. To prove the statement, we just have to take the reciprocal of both sides. Y is going to be greater than 1 over n, and we are done. So we have proven the second part, and like I was saying, this second part especially is a really important result. If I had the sequence 1 over n, this is kind of a preview of sequences. We might not be there yet in the class, but if I have the sequence like 1, 1/2, 1/3, 1/4, which intuitively seems to be getting smaller and smaller, you might be like, well, does it stop anywhere before it gets to 0? And part 2 says no. There's no last term before 0. If there were a last term before 0, like we got to 1 over n in our sequence of real numbers, 1, 1/2, 1/3, stopped at 1 over n. By part 2, we could find another term 1 over like m, where m's a natural number in our sequence, less than this. Well, thank you for watching.